315 meters of rock, clay, and gravel. A height that no residential building reaches in most countries on Earth. Winter temperatures plunge far below -20. The ground shakes because beneath it lies a seismic fault, and this is exactly where someone decided to build the tallest dam on the planet. The mountain did not want this, but nobody asked. Welcome back to the channel. Today we are going to walk through one of the most extraordinary engineering projects ever attempted by human civilization. This is the Shuangjiangkou hydropower station. It stands deep in the mountains of Sichuan Province, in China, on the Dadu River, at an elevation of more than 2,500 meters above sea level, and it holds a title that very few structures on Earth can claim. It is the tallest dam in the world. But this is not just a tall wall stretched across a river. This is a colossal earth and rock structure standing 315 meters high, taller than the Eiffel Tower, taller than any residential building in Europe. Its body is made of 46 million cubic meters of gravel, clay, and stone, packed into a narrow mountain gorge in a seismically active zone in conditions of relentless cold and thin air. This is not just construction. This is not just engineering. This is a war against nature that lasted more than a decade. Let us break down exactly what the engineers were fighting against. The altitude of the construction site is over 2,400 meters. There is less oxygen than at sea level. People tire faster. Machinery performs worse. Concrete behaves differently. In winter, temperatures fall far below freezing. The ground turns to ice. The clay that forms the heart of this dam, its impermeable core wall cannot be placed at sub-zero temperatures because it loses its waterproofing properties when it freezes. The Dadu River is powerful, turbulent, carrying millions of tons of glacial meltwater from the high peaks. Underground, the rock is under extreme internal pressure measured at nearly 38 megapascals. That is one of the highest in situ stress levels ever recorded among comparable projects in China. The rock is not just hard. It is compressed so intensely that when you crack it open, it literally explodes. And all of this sits in a seismically active zone where earthquakes are not exceptions. They are the norm. Freezing temperatures, thin air, a raging river, exploding rock, shaking ground, and they decided to build the tallest dam in the world. Right here. Before we continue, make sure to subscribe to the channel if you enjoy videos about impossible engineering projects. Hit the bell so you never miss a new upload, and stay with us until the end of this video, because what is hidden inside this dam is even more astonishing than its height. When the engineers first arrived at this site, there was nothing. No roads, no bridges, no electricity, no cell signal. Just a narrow gorge carved by the Dadu River, squeezed between jagged mountain ridges. Rock, water, wind. Scattered Tibetan and Qiang villages clinging to the slopes. Wild, harsh, almost untouched land on the border of Markang City and Jinchuan County in the Aba Tibetan and Qiang Autonomous Prefecture to simply deliver equipment to this place. They first had to blast roads through the mountains. To begin construction, they first had to build the infrastructure for construction. Base camps, temporary bridges, power lines, communication towers, water supply systems. All of this at an altitude of 2.5 kilometers, where every breath is a little harder than it should be. The challenge was not a single obstacle. The challenge was that every solution created a new problem. If you build a conventional concrete arch dam like the Jinpei I Dam on the Yalong River, which previously held the world height record at 305 meters. You need perfect rock walls on both sides of the gorge for the arch to press against. But the geology here would not allow it. The rock was fractured, inconsistent, threaded with Lamprof veins and fault zones. An arch dam needs uniform solid abutments. This valley did not have them. If you pour concrete, you need to deliver and place it at enormous heights and at sub-zero temperatures. Concrete does not cure properly. If you build an earth-filled dam instead, you need tens of millions of cubic meters of material, and that material has to come from somewhere. It has to be transported. placed layer by layer, compacted, and all of this in conditions where half the year the ground is frozen solid. So the solution was not simple. It was not a single clever idea. It was a system, a layered, interlocking, almost organic system designed by the engineers at Power China Chengdu Engineering Corporation, the company responsible for the planning, feasibility, studies, survey, and design of this project. They chose to build a gravel, earth core, wall rock fill dam. Let that term sink in for a moment, because understanding it is the key to understanding everything that follows. Imagine a mountain made by human hands. On the outside, massive shoulders of rock and gravel, millions upon millions of tons of crushed stone, carefully sorted by size, placed in precise layers, compacted until it becomes almost as dense as natural rock. This is the mass, the weight, the gravity that holds the dam in place against the pressure of the reservoir. But rock and gravel are porous. Water would seep through them like through a sieve. So running through the very center of this artificial mountain, from the foundation all the way to the crest, is a thin vertical wall of specially prepared clay. This is the core wall, the impermeable membrane. It does not let a single drop of water pass through the body of the dam. The rock on either side provides the strength. The clay in the middle provides the seal. Without the rock, the dam would be pushed away by the water. Without the clay, the dam would leak and eventually collapse. Every element depends on every other element. The rock needs the clay needs the rock, and both need a foundation that does not move. Now let us walk through the construction of this colossus. Step by step, layer by layer, everything began with geological surveying. And this was not a matter of drilling a few boreholes and calling it done. This was years of work. Geologists, seismologists, hydrologists, structural engineers, geotechnical specialists, all converging on this remote gorge to understand what lay beneath the surface. They needed to map the rock structure hundreds of meters deep. Every fault line, every fracture, every layer of sediment, every pocket of weakness. They needed to measure the in situ stress, the natural pressure inside the rock, and the numbers they found were alarming. Nearly 38 megapascals. To put that in perspective, that is the kind of pressure where rock, when exposed by drilling or blasting, does not just crack. It fires fragments at high velocity, like shrapnel from an explosion. This is called a rock burst, and it would become one of the most dangerous hazards throughout the entire construction process. Every meter of tunnel excavation carried the risk of a violent, unpredictable rock failure. Every blast could trigger a chain reaction in the stressed rock mass. The engineering teams had to develop an entirely new classification system for rock bursts, specifically adapted to the conditions at Shuangjiangkou. They installed networks of microseismic sensors, tiny instruments embedded in the rock that listen for the microscopic cracking sounds that precede a major failure. Using advanced signal analysis, including a technique called Hilbert-Wong transform, which extracts instantaneous frequency patterns from the seismic noise, they built a real-time early warning system. When the sensors detected the telltale patterns of an impending rock burst, workers and machinery were immediately evacuated from the danger zone. Minutes of warning, sometimes seconds, but enough. Then came the foundation preparation. Imagine standing at the bottom of a narrow gorge, sheer rock walls rising on both sides, beneath your feet, the river. The first task was to get the river out of the way. Diversion tunnels were bored through the mountain, massive tubes carved through solid rock that redirected the flow of the Dadu River around the construction site. The water thundered through these tunnels while the riverbed below was exposed for the first time in millennia. Raw rock, wet, cold, covered in sediment. Now that raw rock had to become a foundation capable of supporting 315 meters of dam and holding back nearly 3 billion cubic meters of water. The process began with consolidation grouting. Workers drilled holes into the bedrock to a depth of approximately 15 meters and injected pressurized cement slurry into every crack, every fissure, every void. The cement filled the gaps, bonded with the rock, and transformed fractured, unreliable stone into a unified, solid mass, layer by layer. The foundation was healed. But consolidation, grouting only addressed the shallow zone. Beneath that, a far more critical operation was underway. Curtain grouting. This is the creation of an invisible underground wall. Drill rigs bored holes to a depth of approximately 100 meters, far below the foundation of the dam, and injected cement under high pressure. Row after row of boreholes, each one overlapping with the next, creating a continuous barrier of solidified cement deep inside the bedrock. This curtain serves one purpose. It prevents water from seeping beneath the dam. Without it, the enormous pressure of the reservoir would force water through the natural fractures in the rock, undermining the foundation from below. Over time, this seepage would erode the rock, create channels, weaken the base, and eventually catastrophically cause the dam to fail. The curtain grouting at Shuangjiangkou extended to approximately 100 meters below the surface. 100 meters of drilled, injected sealed rock, an invisible wall that no one will ever see, but without which nothing above it would survive. Every borehole was logged, every injection was measured, every meter of curtain was tested for integrity. This was precision work measured in millimeters, performed at the bottom of a gorge. In freezing temperatures, under the constant awareness that the mountain above was not entirely stable, a concrete base platform was poured on top of the prepared bedrock, the physical foundation from which the dam body would rise. Flat, level, engineered to distribute the astronomical weight of the structure above it evenly across the treated rock below. Then came the main event. The filling of the dam body, 46 million cubic meters. Try to imagine that volume. If you took all that material and built a wall 1 meter high and 1 meter wide, it would stretch for 46,000 kilometers. That is longer than the circumference of the Earth. Every single cubic meter had to be quarried, processed, transported, and placed. Rock was extracted from quarries in the surrounding mountains. Gravel was crushed, sorted by size fraction, washed. The clay for the core wall, a special material with precisely calibrated composition, was quarried separately and stored under controlled conditions to preserve its moisture content. And here is where this project becomes truly extraordinary. The clay core wall, the heart of the dam, a thin vertical barrier of specially prepared clay running through the entire height of the structure. It must be absolutely impermeable. Not a single drop of water can pass through it. But clay is a temperamental material at sub-zero temperatures. The water inside the clay S-pores turns to ice crystals. These crystals expand, destroying the microstructure of the clay, opening tiny channels through which water can later penetrate. And in winter, at an altitude of 2.5 kilometers, the temperature is consistently below zero. This means that standard practice stopping clay placement during winter would cost several months of work every single year. Over the course of more than a decade of construction, that adds up to years of lost time, years of delayed completion, years of additional cost. And so the engineers did something that had never been done before in the history of hydropower construction. They used heliostats, solar mirrors. On the slopes of the gorge, above the dam construction site, they installed arrays of computer-controlled mirrors. These mirrors tracked the sun across the sky. The focused beams of reflected sunlight raised the temperature of the soil in the placement zone by more than 5 degrees Celsius. 5 degrees. That is the difference between frozen ground and workable ground. 5 degrees is the difference between shutting down for winter and continuing operations through the coldest months. 5 degrees is months of saved time. This was the first time in the history of dam construction that heliostats were used to heat a construction surface. A technique borrowed from solar energy, adapted for civil engineering, and deployed at an altitude where most people would struggle to breathe, but the mirrors were only part of the solution. Alongside them, engineers deployed massive air, supported membrane structures, essentially enormous inflatable domes that covered sections of the dam surface, creating sealed temperature, controlled environments beneath them. Under these domes, the clay remained within its required temperature range, and placement continued even during the harshest winter months. In addition, specialized air supported membrane storage facilities were built to protect the stockpiled clay from rain and frost. Every kilogram of clay had to arrive at the placement point in perfect condition. Too wet, and it would not compact properly. Too dry, and it would crack. Too cold, and it would be ruined. The logistics of keeping this material alive, and that is exactly how the engineers thought of it, as keeping the clay alive required a level of environmental control that had never been attempted at this scale. The placement process itself was a marvel of precision. Each layer of fill material, whether rock, gravel, or clay, was spread at a specific thickness. Each layer was compacted by heavy rollers. But at this altitude, at this scale, with these volumes, manual control of the rolling equipment was too slow, too imprecise, and too dangerous. And here, the Shuangjiangkou project became a pioneer in smart dam construction. A 5G network was deployed across the entire construction site, unmanned vibratory rollers. Massive compaction machines with no human operator on board were controlled remotely via 5G signal. The system automatically tracked the number of passes each roller made over every square meter of surface. It monitored the pressure, the speed, the trajectory. Not one extra pass. Drones equipped with laser scanners flew over the site, generating three-dimensional surface models in real time. Each completed layer was compared against the digital design model. A deviation of a few centimeters triggered an automatic stop for correction. This was the world's first intelligent production system for dam core wall material, a fully automated chain from quarry to placement. Every cubic meter mattered. Every layer mattered. Every pass of the roller mattered. The filling proceeded month after month, year after year. Layer upon layer, the dam rose from the gorge floor. 10 meters, 50 meters, 100 meters, 200 meters. Each meter higher meant greater pressure from the material below, greater weight on the foundation, greater consequences for any error. The engineers monitored the dam's behavior continuously. Thousands of sensors embedded within the fill material transmitted data on settlement, displacement, pore water pressure, and temperature. The dam was not just being built, it was being listened to. Every groan of shifting rock, every whisper of water movement, every millimeter of compression, all recorded, all analyzed. But the body of the dam was only half the story. Beneath the surface, underground, another battle was raging. The underground powerhouse. Imagine a cavern, not a natural cave, a cavern carved out of solid rock by human hands. Deep inside the mountain, far below the surface, in rock that is pressing inward from every direction with a force of nearly 38 megapascals. Inside this cavern, 4 gigantic Francis turbines would be installed, each one rated at 500 megawatts. Built by Dongfang Electric, one of the largest power equipment manufacturers in the world. 4 turbines, 2,000 megawatts of total installed capacity. Along with the turbines, generators, transformers, cooling systems, cable tunnels, water intake shafts, emergency discharge systems, ventilation, drainage, fire suppression, monitoring equipment, and control rooms. All of it inside a mountain. Excavating these cavities was one of the most hazardous phases of the entire project. Remember the rock burst we described earlier, the phenomenon where compressed rock, once exposed, explodes outward with violent force. In the underground powerhouse, this was not a theoretical risk. It was a daily reality. The rock at this depth is under the same crushing 38 megapascal stress. Every detonation, every borehole, every removed slab redistributed that stress across the remaining rock. And when the stress exceeded the rock's breaking point, the walls fought back. Slabs detached and launched into the cavern at lethal velocity, without warning. Without mercy, the engineers at Shuangjiangkou encountered frequent rock bursts during the excavation of the underground powerhouse complex. The main powerhouse cavern and the auxiliary powerhouse experienced the most severe rock burst activity. The tail race surge chamber was the least affected. But across the entire complex, the threat was constant. The geological challenges did not stop at high stress. The rock mass was cut by unfavorable geological structures, including lamprifier veins and the F1 fault, which weakened the mechanical properties of the surrounding rock in localized zones. Blasting during excavation did not just remove rock, it released stored energy, triggering secondary rock bursts in nearby zones. A chain reaction. One blast could cause failures, meters, or even tens of meters away from the blast site. To fight this, the engineering teams deployed every tool available. Microseismic monitoring networks were installed throughout the underground complex. Hundreds of sensors embedded in the rock walls listen continuously for the tiny acoustic signals that precede a rock burst. Advanrovs process these signals in real time, identifying the location, depth, and severity of the developing failure. When the pattern matched the signature of an imminent rock burst, alarms triggered immediate evacuation. Workers cleared the area. Machinery was moved, and then the rock exploded. Sometimes the warnings came minutes in advance, sometimes only seconds, but every second counted. The walls of the caverns were reinforced with hundreds of rock anchors. Steel bolts drilled deep into the surrounding rock and grouted in place. Rock cables, long-tension steel strands, were installed to bind large blocks of potentially unstable rock to the stable mass behind them. Shotcrete, a layer of sprayed concrete, was applied to exposed rock faces to prevent small fragments from detaching. In the most problematic zones, additional reinforcement was installed. Steel mesh, fiber, reinforced shotcrete, and systematic anchor patterns designed to convert the fractured rock around the cavern into a self-supporting arch. Every meter of excavation followed a strict cycle: drill, blast, ventilate, inspect, monitor, reinforce, then drill again. Slowly, carefully. No unnecessary blasts, no shortcuts. The underground powerhouse was not dug, it was sculpted, carved from hostile rock with the patience of a surgeon and the caution of a bomb disposal team. Then came the flood discharge system. A dam 315 meters tall creates behind it a reservoir holding approximately 2.9 billion cubic meters of water. That water must be controlled, especially during the monsoon season and the spring glacier melt. When the Dadu River transforms from a powerful current into a roaring torrent, the reservoir fills. The water level rises, and if there is no way to release that water safely, the pressure builds until something breaks. And when a dam 315 meters tall breaks, everything downstream ceases to exist. So the discharge system is not an accessory. It is not a secondary feature. It is as critical as the dam itself. The maximum flood discharge head at Shuangjiangkou reaches 250 meters. Think about that number: 250 meters of vertical drop. Water falling from that height accelerates to extraordinary velocities. By the time it reaches the bottom of the discharge channel, it carries enough kinetic energy to shred steel, to carve through solid rock like a river carves a canyon, except not over millennia, but over hours. The erosive force of high-velocity water is one of the most destructive phenomena in civil engineering. A rough surface, a small imperfection, a tiny crack, and the water grabs it, pulls it apart, widens it, deepens it within days. A minor surface flaw can become a catastrophic structural failure. To handle this, the engineers built flood discharge tunnels of a scale never before seen in hydropower construction. These are the largest section discharge tunnels ever built for a hydropower project in the world. Massive tubes bored through the mountain designed to swallow enormous volumes of water. The gates controlling the flow through these tunnels are operated by the world's largest capacity hydraulic hoists. Mechanical systems powerful enough to raise and lower steel gates weighing hundreds of tons against the full pressure of the reservoir. But building the tunnels and the gates was only part of the challenge. Water moving at the velocities generated by a 250-meter head does not flow gently. It hammers. It vibrates. It creates cavitation, tiny vacuum bubbles that form and collapse against surfaces with explosive force, pitting and eroding even hardened materials. To withstand this, the interior surfaces of the discharge tunnels were lined with a special type of concrete that the engineers called mirror concrete. This was not ordinary concrete. It was formulated to be exceptionally smooth, exceptionally hard, and exceptionally resistant to cracking. The surface was finished to a mirror, like polish, hence the name. Every square centimeter was inspected, every joint was sealed, every transition from one section to the next was blended day in, leaving no edge, no lip, no roughness for the water to attack. The goal was simple in concept and extraordinarily difficult in execution. Create a surface so smooth that the water slides across it with minimal friction, minimal turbulence, and minimal erosion. A surface that could endure decades of high-velocity water bombardment without failing. Every centimeter of that surface mattered. Every joint mattered. Parallel to the main dam and its hydraulic systems, an entire world of supporting infrastructure was being built. Roads carved through mountains. Power transmission lines to feed electricity to the construction site itself. Because you cannot build a power plant without power. Worker camps with housing, canteens, medical facilities, and recreation areas. All at an altitude where the air itself fights against you. Quality control laboratories where every batch of clay, every load of gravel, every mix of concrete was tested before it was placed. Equipment repair workshops, fuel storage, communication systems. And then there was the transport and mixing system, one of the unsung marvels of the entire project. Ultra-long-distance conveyor belt systems climb from the quarries at lower elevations to the dam crest hundreds of meters above, carrying millions of tons of fill material on a continuous loop. At the top, the material entered a blending and distribution system where different fractions of rock, gravel, and clay were combined in exact proportions before being spread and compacted on the dam surface. Each component, stones of a specific size, range, gravel of a specific grain distribution, clay at a specific moisture content, and plasticity was delivered in the right quantity at the right time to the right location. An error in proportions, and the layer would not bear the load. An error in placement, and a weak zone would form inside the body of the dam. The system operated like a factory production line, except the factory was a mountain gorge, and the product was a structure taller than any skyscraper in most countries. Years passed, the dam rose, meter by meter, layer by layer, and then, in May of 2025, the moment of truth arrived. The reservoir began to fill. The diversion tunnels that had carried the Dadu River around the construction site for years were sealed. The river returned to its natural path and met the dam. Water began pooling behind the structure, climbing higher with each passing day. The level rose approximately 80 meters above the original riverbed in those first weeks of impoundment. 80 meters of water pressing against the dam face. Billions of liters of accumulated force. This was the first real test of everything that had been built. Not a calculation on a computer screen, real water, real pressure, real consequences. Thousands of sensors embedded throughout the body of the dam came alive. Data streamed in continuously. Water pressure on the upstream face. Seepage rates through the clay core wall, or rather the absence of seepage. Internal deformations, settlement, poor water pressure within the fill material, temperature variations. Every millimeter of movement was tracked in real time by the monitoring system. Engineers watched the numbers around the clock. Any anomaly, any unexpected spike in pressure, any sudden shift in settlement patterns would trigger an immediate investigation. The dam held the clay core wall performed exactly as designed. The gravel and rock shoulders absorbed the water pressure and transmitted it safely into the foundation. The curtain grouting 100 meters below prevented under-seepage. The consolidation grouting in the upper foundation zone maintained the integrity of the contact between the dam and the bedrock. Every system worked, every layer held. By this point, the dam body had reached a height of approximately 260 meters. This was sufficient to begin power generation from the first turbine unit, even though the dam had not yet reached its full design height of 315 meters. The remaining 55 meters will be added in the coming period, with the dam body planned to reach its full crest elevation of 2,510 meters above sea level. But the station did not need to wait for the final meter. It was ready to produce power. On the 26th of June, 2026, the first generating unit at Shuangjiangkou was connected to China's national power grid. 500 megawatts of clean, renewable electricity surged into the system. Water from the reservoir, stored at enormous height, flowed through pressure tunnels deep inside the mountain, accelerating as it dropped and slammed into the blades of a Francis turbine built by Dongfang Electric. The turbine spun, the generator turned, the kinetic energy of a glacial river was converted into electrical current. No coal was burned. No gas was ignited. No carbon dioxide was released. Just water, gravity, and engineering. When all 4 generating units are fully operational, the Shuangjiangkou hydropower station will produce approximately 7.7 billion kilowatt-hours of electricity per year. That is enough to power millions of homes, enough to displace millions of tons of carbon emissions that would have been produced by fossil fuel plants. Generating the same amount of energy, but the significance of Shuangjiangkou extends beyond its own output. This station is the head facility, the controlling station of the entire cascade of hydropower plants along the Dadu River. Its reservoir regulates the flow of the river downstream. During the wet season, it stores excess water, preventing floods that would devastate communities along the lower Dadu and the upper Yangtze. During the dry season, it releases stored water, maintaining river flow and ensuring that the downstream hydropower stations can continue generating electricity even when natural rainfall drops. Without Shuangjiangkou, the entire Dadu River cascade operates less efficiently, less reliably, less safely, with Shuangjiangkou in place. The entire river basin becomes a managed system, a chain of stations working in concert, each one enhanced by the presence of the dam above it. Without it, floods, waste, unpredictability. With it, control, clean energy, and a river that serves the people instead of threatening them. Stop for a moment. Consider the scale: more than a decade of construction. 46 million cubic meters of material placed, 315 meters of height, a construction site at 2.5 kilometers above sea level, a seismically active zone where the ground shakes without warning, underground rock with nearly 38 megapascals of in situ stress enough to trigger violent rock bursts at any moment during excavation, winter temperatures far below freezing, thin air that saps human energy and degrades machine performance, a raging river that had to be diverted, contained, and ultimately harnessed. And from all of this, a working power station that converts a mountain river into clean energy for a nation. Most people who will ever see this dam will see only the wall, a massive, imposing wall stretched across a gorge, and behind it the still surface of a reservoir reflecting the mountains and the sky. That is all they will see. They will not see the clay core wall running through the entire height of the structure, a thin, invisible membrane separating billions of tons of water from dry rock. They will not see the curtain grouting 100 meters below the foundation, an underground wall of injected cement that no human eye will ever look upon, but without which the dam would be undermined and destroyed. They will not see the underground powerhouse carved into the heart of the mountain, where 4 turbines spin in perpetual darkness, converting falling water into light and warmth for millions of homes. They will not see the scars of rock bursts on the walls of the underground caverns, places where the mountain tried to close the spaces that humans had opened inside it. They will not see the heliostats on the slopes above the dam, solar mirrors that caught winter sunlight and bent it downward to warm the freezing clay, so that construction could continue through months when all logic said it should stop. They will not see the thousands of sensors embedded in every layer of the dam, sensors that are transmitting data right now, at this very second: pressure, temperature, displacement, seepage, settlement, a continuous stream of information flowing from inside the structure to the engineers who watch over it. They will not see the unmanned rollers that compacted every square meter of the dam's surface with a precision no human operator could achieve. Guided by 5G signals across a construction site where there had once been no roads, no power, no signal of any kind, they will not see the mirror concrete inside the discharge tunnels, polished to a flawless sheen, designed to withstand the impact of water falling from a height of 250 meters. They will see a wall and a lake, and perhaps the mountains. But now you know what is hidden behind that wall. Now you know what lies beneath it, inside it, and around it. Now you know the decade of work, the thousands of decisions, the millions of tons of material, the technologies invented specifically for this project, and the relentless battle against a mountain that did not want to be tamed. There are projects that are built for profit. There are projects that are built for prestige. And then there are projects that are built because someone looked at an impossible challenge and refused to look away. The Shuangjiangkou Dam is the answer to a question that nature asked engineers for decades. Can you build here? Can you build at this altitude? In this cold, on this fault line, over this river, inside this rock? And the answer, delivered in 46 million cubic meters of stone, clay, and gravel, reinforced with steel, monitored by sensors, guided by satellites, heated by mirrors, and compacted by robots, was yes. Yes, in the freezing mountains. Yes, on the shaking ground. Yes, above the raging river. Yes, with mirrors and drones, and artificial intelligence, and technologies that did not exist when this project began. 315 meters, the tallest dam in the world, built where a mountain resisted every single day. And the engineers came back every single morning. That is not just construction. That is not just engineering. That is a statement about what human beings are capable of when they commit to something fully, completely, and without reservation. If you enjoyed this video, subscribe to the channel and hit the notification bell. Leave a comment below and tell us which engineering mega project you would like us to cover next. Share this video with someone who appreciates what humans can build, and thank you sincerely for watching until the end. We will see you in the next one.